Hello and welcome to all of you. We are in the discussion of the hydraulic turbines, and so far in the earlier two videos, we have discussed the various aspects which are associated with the impulse hydraulic turbine. So that was nothing but the Pelton wheel. We have also discussed regarding the operating principle which is used for the governing of the impulse hydraulic turbines. Now, taking this topic to the next part of the hydraulic turbines, we will now focus on the radial flow reaction turbines. So let us see what the radial flow reaction turbines are indeed. The radial flow reaction turbines are those types of the turbines in which the water flows in the radial direction. Okay, the flow of the water that is in the radial direction. It may be possible that the water may flow radially from outward to the inward. Okay, from the outward to the inwards. It means that toward the axis of rotation of the shaft. Alternatively, the flow of the water may be from inward to the outward. It is away from the axis of the rotation. Okay. If we see the first arrangement, that is the water that is flowing from the outward to the inwards toward the runner, then we identify such types of the turbine as inward radial flow reaction turbine. And consequently, if the water flows from inward to the outward, we identify such types of the turbine as the outward radial flow reaction turbine. Okay, so we are having the two configurations for the radial flow reaction turbines: inward radial flow and outward radial flow reaction turbine. So what are the main characteristics features as far as the radial flow turbines are concerned, or the reaction turbines are concerned rather? The reaction turbines are nothing but the turbines in which that the water at the inlet of the turbine that possesses both the types of the energy. It means that the kinetic as well as the pressure energy. And we clarified that in case of the impulse turbine, the energy which is possessed by the water at the inlet of the turbine was only the kinetic energy. But in case of the reaction turbine, so it is both kinetic energy as well as the pressure energy. And whereas the water that flows through the runner in case of the reaction turbine, so it is associated that the part of the pressure energy that goes on changing into the kinetic energy. So there is a gradual conversion from pressure energy into the kinetic energy. So due to this fact, the water which is flowing through the runner, so that is under pressure in case of the reaction turbine. The additional feature that can be identified there for the radial turbine, reaction turbine, the runner is completely enclosed in an airtight casing, and the casing as well as the runner, they are always full of water. So that may not be as such the feature as far as the impulse turbine are concerned. Okay, I repeat here, the runner is completely enclosed in an airtight casing, and the casing in addition to the runner, so they are always full of water in case of the reaction turbine. So one of the important type of the reaction turbine is nothing but the Francis turbine that one can see here as such. Okay, so Francis turbine is a widely used type of the reaction turbine, so that help us for the efficient conversion of both pressure and kinetic energy into the mechanical energy. The Francis turbine can also be identified as a mixed flow reaction turbine. Okay, during the classification of the turbine, we have seen this particular fact. So water enters the turbine radially and leaves axially, okay, and thus allowing the smooth and effective energy conversion for the water into mechanical energy. The Francis turbine are normally suitable as far as the medium head arrangement is concerned. Okay, so anywhere the head that ranges between the 40 meter to 600 meters. Okay, so those are the medium head type of the turbine, and the features such as the high efficiency, reliability, and versatility. So such feature make them an ideal choice for the operation of the modern hydroelectric power plants. The block diagram for the Francis turbine that can be seen in this slide, and as far as the important components, for the radial flow reaction turbine are concerned, so we are having the four main parts, essential parts. Namely, those parts are the casing, then the guide mechanism, the runner, and the draft tube. Okay, we are having the casing, the guide mechanism, the runner, and the draft tube. So they can be seen as such in this arrangement. We are having the scroll casing here as such, then the guide vane or the wicket gate, so which is the for the guide mechanism. Then we are having the runner, so which is mounted there at the center, the main shaft, and toward the outlet of the turbine we are having this increasing cross section area, so that is nothing but a draft tube, okay, whose area goes on increasing gradually from inlet to the outlet side, okay, that is toward the tail race side. It can also be seen that the last portion of the draft tube, so that is immersed there into the tail race as well, isn't it? So let us see what are the important features which are associated with these four important parts of this Francis turbine. Now, as far as the casing is concerned, we are aware that the casing and the runner, they are always full of water. Okay, so this may not be the feature there in case of the impulse turbine. The water that is admitted from the penstock that enters into the casing is normally of the spiral shape. Okay, spiral shape, and it is also characterized that the area of the cross section for the casing that decreases gradually. Okay, the area of the cross section for the casing that decreases gradually. The casing that completely surrounds the runner in the turbine. Okay, the casing that is made of the spiral shape, so that the water may enter the runner at the constant velocity throughout the circumference of the runner. So that is what the essential feature of the casing is there. The different types of the materials such as the concrete, the cast steel, plate steel, these are some of the materials which can be used for the construction of the casing for the Francis turbine. As far as the guide mechanism of the Francis turbine is concerned, so it will consist of a stationary circular wheel, okay, all around the runner of the turbine. The stationary guide vanes which are as such shown here, okay, on left side, similarly there onto the right hand side. So the stationary guide vanes are fixed on the guide mechanism, and these guide vanes, so they allow the water to strike the vanes fixed on the runner, so without any shock at the inlet. It is also possible that by a necessary or suitable arrangement, the spacing between the two adjacent or the width between the two adjacent vanes of the guide mechanism, so that can be changed according to the requirement. So this feature that allows us for the variable amount of the water that is striking the runner, isn't it? It means that the discharge which is striking the runner, so that can be changed according to the requirement by adjustment of these vanes of the guide mechanism. Another important component is the runner. So in some of the previous slides we have seen the shape of the runner for the Pelton wheel, whereas the runner, it is nothing but again here a circular wheel, and on the periphery of which a series of the radial curved vanes, they are normally fixed. Okay, it is also essential that the surfaces of these vanes are made very smooth, and they are so shaped in such a way that, okay, these vanes are shaped in such a way that the water enters and leaves the runner without the shock. So it means that the losses can be minimized, and that's why the shape of this radial curved vanes is made in that fashion. The different materials such as the cast steel, cast iron, or the stainless steel, so that can be used for the manufacturing of this runner, and this runner are normally mounted there onto the shaft. You can see that the main shaft, so this main shaft is nothing but placed in the vertical fashion, isn't it? So this is nothing but the main shaft that is vertical, and around the periphery of this we can have the runner. It will be also interesting for us to show this arrangement this into this particular slide. So on the top right side, whatever the green color pipe that we can see, so that is nothing but the casing of the gradually reducing area. Okay, so this is the runner that we are having. Then these are nothing but the guide vanes, so they properly guide the flow of the water from the casing toward the runner. Then we are having the main shaft that is placed in the vertical fashion, and on the outlet side, so it is nothing but the draft tube that can also be seen. The picture which is there onto the bottom left corner, so that is nothing but the runner of the Francis turbine, isn't it? And number of blades which can be seen placed around the periphery, they are equally spaced, isn't it, around the periphery of this runner. So this is nothing but the outer periphery, inner periphery. So if the water enters at outer periphery, leaves at inner periphery, that is the inward flow radial turbine, and vice versa of that one, isn't it? So that will enter into the inner periphery, water will enter into the inner periphery and will leave at the outer periphery. Okay, outward radial flow reaction turbine. The fourth important component that we have is nothing but the draft tube, isn't it? The fourth important element. So we can see that this portion, okay, toward the outlet side of the Francis turbine is nothing but the draft tube. Okay, so it is that the pressure at the outlet of the runner, at the exit of the runner of, or in case of the reaction turbine, is usually less than that of an atmospheric pressure, isn't it? Whereas in case of the impulse turbine, okay, after the water being discharged to the tail race side, so the pressure is nothing but the atmospheric. So this is not the case as far as the reaction turbines are concerned. Okay, so this pressure is generally less than that of an atmospheric pressure. So hence the water at exit that cannot be directly discharged to the tail race, isn't it? So this arrangement can be easily possible for the Pelton wheel, right? So hence what we do here, we normally utilize a tube, or let us say a pipe of the gradually increasing area, okay, from inlet to outlet. So that is essentially used to discharge the water from the outlet or the exit of the turbine to the tail race, isn't it? And that is why we can see here in the previous arrangement, isn't it, the last portion of this tail race, so that is partially immersed there into the tail race, right? So this is nothing but the tube or the pipe of gradually increasing area, and that essentially helps us to discharge the water from the outlet of the turbine to the tail race. So this tube of increasing area, that is known as the draft tube. So this draft tube is absent in case of the impulse turbine, in case of the Pelton wheel. Alright. So these are the four important components, or we can say the constructional features, constructional arrangement as far as the Francis turbine is concerned. It will be also interested to us to show or to throw some light there onto the draft tube, isn't it? So we have seen that the draft tube is the integral part of the reaction turbine, and we are quite aware that the pressure at the exit of the runner in case of the reaction turbine is generally less than the atmospheric pressure, right? So due to this reason, we are aware that the water cannot be directly discharged to the tail race in case of the reaction turbine, and hence we utilize the pipe of gradually increasing area, so with the help of which we discharge the water from the exit of the turbine to the tail race. So one end of that draft tube is connected to the outlet of the runner, isn't it? So this is what the turbine casing, and this is the inlet of the draft tube. So one end of the draft tube, okay, so this end of the draft tube, so that is nothing but connected to the runner or to the casing, whereas the other end, that is nothing but this lower end, isn't it? So this is the outlet of the draft tube. Okay, the other end of the draft tube is submerged below the level of water in the tail race. So this is the level of the tail race, okay, and the last portion of the draft tube, so that is submerged below the level of the tail race. The draft tube, in addition to serve as a passage for the discharge of the water, so it also serves some other purposes as well. Okay, the other important functions which can be performed by the application of the draft tube, so we can identify them as the pressure recovery. Okay, so it converts the high kinetic energy, that is velocity of the water which is leaving the turbine, which is leaving the runner, into useful pressure energy. It reduces the velocity of the water as it leaves to the tail race, and thus minimizing the loss of energy. The draft tube that also help us for the increasing the efficiency, okay, because it increases the total head which is available for the turbine. Okay, so higher being the head, so that help us to achieve the higher efficiency as well as the power output from the turbine. It also offers the flexibility in the installation. Okay, the addition of the draft tube, so that allows the turbine to be placed above the tail race. And if such is the arrangement, so that is definitely beneficial for us as far as the maintenance of the draft tube that is taken into consideration. Okay, so these are say some of the important benefits or the advantages that we can say we can obtain from the application of the draft tube in case of the reaction turbine. So what are the different types or the arrangements for the draft tube which can be utilized for the operation of the reaction turbine? So we will have a quick look on the different geometries, different types of the draft tubes. So one of the arrangement that is shown here is nothing but a conical draft tube. Okay, so it is commonly used for use as a hydraulic component in the reaction turbines. The conical shape that features a gradual expanding cross-section area from the inlet to the outlet. So that is a bit obvious, can be seen from the sketch there. This design helps us to effectively convert the high velocity, that is the kinetic energy of the water leaving the turbine, into useful pressure energy. The conical draft tubes are suitable. Okay, they are adaptable as far as the low to moderate load conditions, and they are known for their simplicity in design, maximizing the efficiency in the operation of the turbine. The another configuration arrangement that can be utilized as a draft tube is nothing but the simple elbow draft tube. We can see the arrangement for the simple elbow draft tube here. So this tube is essentially characterized. It is identified by a sharply curved bend. Okay. So it actually resembles to an elbow that is connecting the turbine exit to the tail race. This particular arrangement that helps us a compact installation, and it makes us suitable for the sites with the space constraint, wherever there is a limitations in the space. So simple elbow turbines, simple elbow draft tubes, so can be suitable for such arrangements or the such situations. In addition to that one, even though the simple elbow draft tube may not be as efficient for the other type of the energy conversion, but it still remains a practical choice for the applications where the space considerations are of significant importance, right? This one is another configuration that we identified as a moody spreading draft tube. So we can see that one inlet and there are the multiple outlets, isn't it? So this moody is nothing but a spreading draft tube that incorporates a gradual transition from the turbine exit to a wider and flared outlet. So we are having the two outlet and one inlet as such. Such characteristics in the design that helps to optimize the conversion of the kinetic energy into pressure energy, and this helps us to improve the turbine efficiency as far as such arrangement is concerned. Now this moody spreading draft tube, they can be utilized, they are more popular as far as the medium to medium head hydroelectric power plants are concerned. It is also suitable to maintain the optimal flow profile and thus minimizing the energy losses. Okay, so these are some of the important features as far as the moody spreading draft tube is concerned. The fourth configuration that we can see here, that is a draft tube with the inlet that being a circular. Okay, the circular is the inlet, and if we see the other end, that is outlet, so it is nothing but the rectangular one. Okay, so such arrangement is the draft tube with the circular inlet and the rectangular outlet. Okay, so they can be used to adapt the different flow conditions. I mean to say that the circular inlet that helps to smoothly guide the water from the turbine, okay, from the inlet, whereas the rectangular outlet that allows the controlled expansion and energy conversions. Okay, so these are nothing but important characteristic features for such type of a draft tube. So this flexibility, versatility, that makes it suitable for the hydropower applications which are subjected to the different heads, the variable heads and the flow conditions, and while maintaining the efficiency, high efficiency in the energy conversion or the energy transfer. Okay, so we'll stop here as far as this particular session is concerned. We have talked about the reaction turbines. We have identified the difference between the inward radial flow reaction turbine and outward radial flow reaction turbine. And we have also seen the constructional features and the operating principle as far as the reaction turbine is concerned. So Francis turbine is one type of a reaction turbine. So having a vertical, what you can say, the vertical position, vertical axis of the shaft. The Francis turbine is suitable for the medium head applications as well as the medium discharge as compared to that of let us say the impulse turbine. Okay, so we'll stop here for the today's session. The other topics which are associated with the hydraulic turbines, so that we'll discuss in the next portion. Thank you very much for your kind attention.